All right, welcome back to the next lesson on resonance structures. So basically, we're still writing Lewis dot structures. Okay, this lesson is going to be very similar to the last lessons. We're going to be starting out with all the same steps and procedures of writing a Lewis dot structure, and it could even be for a polyatomic ion too. But the point is, we're going to get to the very end, and we're going to realize, we have some options. We could move these electrons, or we could move these electrons. And so because of that, we have to address that with what are called resonance structures. I hope you guys know what the word resonance means. Resonance means to bounce back and forth. So like to alternate back and forth, resonate. A lot of people say, well, I really resonate with that. That means it's like the frequencies are the same. There's a nice back and forth dialogue that resonates, or noises will resonate too. They will bounce back and forth and come back and forth, and it's called resonance. And so you want good resonance. If you have like an instrument like a guitar, you want the vibrations to resonate really well in the acoustic wooden drum. You want the sound waves to resonate back and forth and resonate with each other real well, the waves to do that. And so that term is sort of relevant for, you'll see this lesson. Follow with me in the book here, 10.6. Again, when you're writing the Lewis structures, you're going to find that sometimes there's more than one good Lewis structure. All right? And for example, let's say you have SO2. This is not SO2 with a minus charge or anything like that. Be careful what you're looking at, because there is such a thing as SO2 with a -1 charge. But this is just SO2, sulfur dioxide. We would first write the skeletal structure like this, remembering that we want some symmetry, and so it just makes sense to put the 2 oxygens just outside of the sulfur. And then the next step would be to add up all your valence electrons. Well, each of the oxygens have 6, so there's 12, and sulfur has 6 as well, right? So, wait, what? Yeah, sulfur has 6 valence electrons. It's just in another period. Sorry. Drew a blank there. So they have different proton numbers, but they do have the same valence electrons, the outermost electrons. And so it's basically 6 times 3. They wrote it this way because this illustrates the oxygen component, the 2 oxygens at 6 apiece, and this represents the sulfur component. But 6 times 3 would still give you 18. That means that's how many electrons you must represent. No more, no less. And what you're going to do is first place them where the bonds are. So we have a bond between these 2 atoms and a bond between these 2 atoms. So we need to show a pair of electrons there. That gave us 4. That's used up 4 of our electrons. Now we're going to distribute the remaining ones to the terminal atoms first. So all our outside atoms will distribute our electrons. And again, it's a good idea to keep some balance. So give 2 to this one, and give 2 to this one, and 2 to this one, and then 2 to this one, and then 2 to this one, and 2 to this one. At the end of the day, though, it doesn't matter. You're going to end up usually with this structure right here. Okay? And check it out. The oxygens actually got their octets, didn't they? They're happy. But the central atom did not. But that's okay, because it said in our steps, we're not supposed to worry about the central atom until towards the end anyway. And so since the central atom lacks an octet, you remember what we do? We borrow from the terminal atoms. And so it doesn't matter where we start. Let's just start from the left side. Let's borrow these 2 electrons and put them here. So that, remember, that means that when we have a double bond there, these 2 electrons actually we get to count them for the oxygen, and we get to count them for the sulfur. So check it out. If we draw a little circle there or whatever, we get to count 2, 4, 6, 8 for the sulfur, and 2, 4, 6, 8 for the oxygen. And then this oxygen on the right is already happy with 8, right? So boom, everybody's happy. Check it out. There you go. There's your structure. But couldn't we have just as easily as borrowed the 2 electrons from this oxygen and made a double bond on the right side instead of the left? And then again, everything is happy. Octet, octet, octet. Yes, that's true. Either one would work. This structure and this structure are both equally correct Lewis dot structures, but yet they're different. So they're equivalent to each other, almost equivalent. They're equally as good. And so for that case, we have what's called resonance. In nature, either one of those would work. Either one of those would work. And so the idea is that maybe in nature, these two structures are sort of resonating back and forth from each other. If you were to take a freeze frame picture, a snapshot, and then analyze the molecule, you might see it like this. Okay, and then you take another quick snapshot of the molecule, and you might see, okay, well now it's looking like this. And it's as if the electrons are resonating from here, back to here, to back to there, to back to there. And these structures are basically resonating back and forth from each other. So like they're flip-flopping. One moment it looks like this, and the next moment it looks like this. Never are they in both at the same time, but in fact, what really happens, since these aren't really like particles anyway, since these electrons are not actually like particles anyway, and they're kind of like waves, then really you basically just have energy distribution sort of in between both, and we don't really have a way to represent that since we're using dots, since we're not trying to draw 3D orbitals or anything like that. And so you do have to draw basically just both structures. You just put a bracket around this one, put a bracket around, no, we don't use brackets, do we? Because we're not drawing an ion. Yeah, so this is fine. So boom, there you go. Let's look at this one though. This is an ion, a nitrate ion. So remember, these, we do have brackets. You always have brackets around ions. When you write a Lewis dot structure, it's an ion that has a charge, put brackets around it, and then put the charge. Okay, so nitrate, nitrogen with 3 oxygens, will have somewhat of a skeletal structure like this. Now, if you put this oxygen on the bottom instead of the top, no big deal. It doesn't matter. There's no such thing as a top and bottom anyway to a molecule. It just depends on how you're looking at it. And so let's just go with this structure here. Or likewise, you could have this one here on the bottom and have nothing on the right. It doesn't matter. Basically, to keep it symmetrical, we want the nitrogen in the middle and all the oxygens surrounding it. All right. And so let's do the math first. How many electrons are we allowed to use? And that actually rephrase that, how many electrons must we use? So you have no choice but to use the valence electrons you have to work with. And oxygen's at 6 apiece, times 3 is 18, and then nitrogen has 5. So 18 plus 5 plus the extra electron that's in the ion gives us 24. All right, so we got 24 electrons that we can and have to use. And we are going to start, if you remember, with the bonds. So there's a bond between this oxygen and nitrogen. There's a bond there and a bond there. Put those electrons there first. That's going to be 2, 4, 6 electrons total. But remember, I need to show 24, so I'm not done. I keep putting down my electrons on the terminal atoms, on the outside terminal atoms. That's what outside or terminal means, was on the outside. Maybe start here and then add a pair there and add a pair there, then go back to this oxygen and just kind of alternate whatever. But at the end of the day, when you're done showing your 24 electrons, you're going to have this structure where basically all 3 of the oxygens got octets, didn't they? That's what it says to do. Place all the distribute the remaining oxygens first to the terminal atoms, trying to give everything an octet. Then so you have 2 things you could do here. If there are no electrons remaining, remember, then you're allowed to form double bonds or triple bonds as necessary. If you have any extra electrons, then you put them on the central atom. I don't know if we've addressed an example like that yet, but in this case, we need some extra electrons, so I'm going to have to borrow. Where do I borrow from? Do I borrow from this oxygen up here? Do I borrow from this oxygen down here on the left, or the oxygen on the right? It could be either, all 3 of them. So literally, you're going to need a double bond either on the left, the top there, or on the right. One of them, do you need to draw? And actually, check this out, guys. You're going to hate this. I'll have a few of these on the test, but not tons. But I at least need to know that you know about resonance structures and what they mean. and you actually have to draw all three. You actually have to draw all three. Since all three Lewis structures are equally correct, then you literally have to write all three structures. And you put these little arrows saying, you know, it's going to go back and forth. It's either going to be like this or like this or like this. And so you have to show all three. Later on, I will show you. Oh wait, you know what? I'm going to show you this now. For those privileged enough to watch this video, I'm going to show you how to write a resonance structure, a little shortcut. And so, since you're watching my videos, I'll allow you to do this. Resonance structures for, let's just say polyatomics. It doesn't matter. This could be for any, doesn't have to be a polyatomic ion, but guarantee you when I see this pulled up on Google Images, I'm going to get something. I'm almost positive. And that's because in real life, we usually use shorthand notation. Well, you'll also see them like this too, where, you know, they literally show every structure. This would be carbonate. You can have the double bond there on the right or up at the top. But another way to do it is like this. So, or like this. Here's a better picture here. What you do is you show a double bond on all three. But one of the lines for each double bond is a dashed line. Basically saying, well, it could be there, or it could be there, or it could be there. So instead of drawing three resonance structures, you can just draw a dashed. One of the lines is solid, but one of the lines is dashed. And basically that dashed line is resonating back and forth between, sometimes it's on that double bond, sometimes it's on that one, and sometimes it's on that one. All right? And so basically the bond length there is 1 1/3 instead of 2, because literally that double bond is shared equally between all the NO3. And this is actually more relevant to quantum. It's more relevant to quantum physics and quantum chemistry, because the structures don't actually resonate back and forth. They don't go from looking like this to then this and then this. That's not actually happening in nature. It's been studied and concluded and determined that we don't have sometimes this structure and then sometimes this structure and sometimes this structure. No, there's just one structure, but one structure that has to represent all three of this at the same time. So what does that look like? How do you distribute some of the energy there, some of the double bond there, and some of the double bond there? Well, you just have to distribute that energy that way in sort of a wave-like frequency or whatever. And so again, but if you're doing Lewis dot structures, which aren't perfectly representative of nature, then this is probably the best way to do it. So not only is this a shortcut, but it's probably like the most relevant as far as like quantum chemistry goes. So instead of drawing all three structures, if you want to show that dashed line, I'm okay with that. Don't forget to show your lone pairs where they go, okay? And remember, everything really technically tries to space itself out as far as possible. So instead of putting these directly on the bottom and this lone pair directly on top, you see they've kind of shifted it a little bit so that these electrons are kind of running away from all of these electrons here. Everything is trying to be as far away from each other as possible. You can even see that in this example. The electrons, you got the widest angles you can get between the electrons. Same with like when you draw this molecule here. Do you see how everything's kind of at a triangle shape instead of down and then just straight to the left and straight to the right? These are running up, trying to get away from this oxygen. So these aren't like up and straight left and straight right is not perfectly accurate. And you'll see that in the next lesson. That's why I'm bringing that up. And so even in organic chemistry, again, we even have another shorthand method. Instead of doing dashed lines all the way around, we'll just do a circle like this. For a benzene ring, you'll just have a circle that says, hey, the electrons are technically resonating all the way around this ring, equally shared. But that's important. It's important that electrons have the ability to be distributed more throughout a molecule rather than being just like stuck in one spot, because it makes molecules either less reactive or more reactive. Just trying to find you more examples of resonance here, that's all. But good. Stay tuned for the next lecture because it's all about, again, the geometry of molecules. And so I look forward to going into that, and I believe, if I'm not mistaken, that is our last lesson in this chapter is about, no it's not, we got electron geometry, molecule geometry, and then how that applies to how atoms and compounds will bond to each other. So the shape of molecules really is important on how molecules will bond to each other, but that's going to be in the next video, so make sure you watch it. Bye bye.